So, I want to talk to you about interesting idea known as gradient boosting. So, all of you remember what boosting is about, right? What is boosting?
You use multiple classifiers which have more than like it just better random combination.
That's bagging. Boosting. Yeah. So boosting is specifically a stage-wise process where at every stage you try to boost the classifier from the previous stage such that the error is minimized, right? Error is reduced, not necessarily minimized, but the error is reduced, right? So that is a characteristic of boosting. So at every stage you have to look at the errors from the previous stage and you are trying to reduce that, right. So we looked at AdaBoost, right, one of the most popular boosting algorithms, and then I told you that AdaBoost uses exponential loss and that it is related to the logistic loss, and so you can actually use the logistic loss function and derive a boosting algorithm which is called logit boost, right, but it is very similar properties to AdaBoost, but AdaBoost is more popular especially from analysis point of view and things like that, because it has got really nice properties. Okay. There is yet another approach to boosting that is gaining a lot of currency recently. Okay, it is called gradient boosting, right, not well recently would mean in the last decade or so, right, compared to AdaBoost which is several decades old, right. So, and sometimes they even call it gradient boosted decision trees, right, gradient boosted decision trees, because so you use this specifically in conjunction with trees, right. And in fact, in many applications now gradient boosted trees are actually getting hard to beat, right. And so just reintroduce some notations that you might have forgotten, right. Right. So, the I is an identity function which is 1 if x belongs to Rj, is 0 otherwise, right, and so this is summing over all regions. So, R1 to R capital J, and gamma j is essentially the output I am going to produce if x lies in Rj, right. This is a regression tree thing. So, my what is my theta here? Right, all the Rj's, the specification of the Rj and the gamma j's for each of those regions. So, that is my theta, and typically we pick some loss function. If it is regression, it is going to be squared loss, and then right. So, I look at the loss incurred when the actual output is yi and the output I am giving you is gamma j. So, for all data points x that belong to a region Rj, the output will be gamma j. So, this is essentially the loss there, and sum this over all regions, and this is right. I am just recapping decision trees for you, right. And then we looked at greedy methods for finding Rj, right, and given an Rj we knew how to fit gamma j, right. So, given that we looked at some greedy search methods, right. So, you can do this, you can do boosting with trees also, just like you did boosting with other classifiers, you can do boosting with trees, right. Right. So, I have m trees. So, essentially I taken sum of the output of all the m trees, that gives me my boosted tree, right. Remember that, I mean, this is not a single tree, okay, it is now a forest, right. I have a collection of trees, a collection of trees is a forest, right. So, it is actually a forest. So, I basically do that, and the difference here is can people at the back see this, right. So, this is essentially when I find the parameters for the mth tree, right. So, I am going to look at the classifier or the predictor that is formed by the first m minus 1 trees, right, and then I am going to find that tree, okay, whose output I will add to this predictor, right, and use that for computing the loss, right. So, for every data point in my training data, right, I look at the yi, I look at the output produced by the m minus 1 stage tree, I look at the value that is added by the mth tree. So, this is the output produced by the mth tree, I look at the value added by the mth tree to that, right, and then I will compute the loss function, okay, make sense, yeah. So, the basic idea is that every point, this is just forward stage wise addition, that we like whatever we did before introducing boosting, right, that is exactly that. So, now this becomes boosting because I am explicitly trying to figure out what the residual error is from here, okay, and trying to adjust for the residual error using my tree, the new tree I am learning, right. So, when will it be the residual error? When it is regression task and squared error is my metric, right. So, when the loss function is squared error, right, and I am trying to solve the regression problem, right, then essentially what I will have to do here is take the residual error. So, whatever the tree does not explain, the m minus 1th stage tree, whatever that does not explain, so that error I will have to explain using this, right. So, if you think about what we are doing here, so you will first build one tree to predict your output as best as possible, right. You predict your function as best as possible, you will build a tree, then what you will do is, okay, you will take the residual of that, okay, build another tree that predicts the residual as well as possible and add the output to this, okay, and then take the combined thing, find the residual of that, build a third tree which will predict the residual and add it back to this, and so on and so forth, right. You just keep doing this, correct. So, that is essentially what boosting in trees means. We have still not come to the gradient boosting part, okay. So, finally it will look very similar to what I am telling you now, but we have still not come to that part yet. So, as with regular decision tree learning, given the RJs, right, finding the gammas is easy, given the RJs finding the gamma j's is easy, right, but the problem is finding the RJs, right. In general it becomes a little tricky, finding the regions becomes a little tricky because I have to take into account the other trees output also, right, in general, right, but when I am talking about squared error it is very easy because things nicely decouple, right. When I am talking about squared error I do not have to worry about f m minus 1 after I compute the residual, right. The residual could have been generated by any classifier, any regressor, right, does not have to, I do not even have to worry about the fact what generated the residual was actually a tree, right. So, I do not have to worry about it, all I need is just the residual becomes any function, right. So, with squared error boosting becomes just like learning a series of decision trees, okay, nothing special about it, but if you have other kinds of loss functions then you will have to worry about how to accommodate that, but at least in this case of squared error loss, okay, So, that is essentially your target function, right, and what will be the gamma hat that you will need? Just be the average residual error in the jth region, right. Is it clear? Any questions? So, in fact, there is another case where it becomes simple, which is essentially, so for 2 class problems, and for 2 class problems and exponential loss functions, what do you think you get? It becomes exactly the same as doing AdaBoost with trees, okay, for 2 class problems. But so it turns out there are tricky things here, right. So, if it is a multi class problem, okay, then things do not decouple as nicely. So, if you have 2 class problems and your loss function is exponential loss, okay, you can show that this is essentially the same, the computation that we are trying to do here, right, that minimization, everything that we are trying to do here will essentially reduce to the same solution that you get if you did the AdaBoost derivation on decision trees, okay. But these are the 2 cases where this thing simplifies, right. For example, if you are trying to use deviance as a loss function, then things do not decouple this easily, okay. So, these are things that you have to keep in mind. So, this is one part, this is essentially telling you how to do boosting with trees the regular way, okay. So, let us look at something else now. So, I suppose I have some differentiable loss function, some loss function which I can take the derivative of, right. So, if I want to take a numerical approach to optimizing this kind of a loss function, so typically what will I end up doing? I will start off with some guess for a solution, right, take the gradient of the loss function with respect to the parameters at that solution point, right. People remember gradient descent, right. Then I will compute the gradient and then I will move in the opposite direction of the gradient, right. I will move a small step in the opposite direction of the gradient, go to a new place and compute the gradient again and then move again and so on and so forth until I converge to the right answer, right. So, if you think about what this is doing, this is something like, okay, I take initial solution, okay, then I add another solution to it, which is essentially the gradient times something, then I add something more to it, so I will add something. So, essentially the solution I am computing finally is a sequence of additions that I have done on the basic solution I started off with, right. So, even though one way of thinking about it is at every point I give you a parameter vector, but the parameter vector itself is composed of a sequence of additions. So, I can think of it as first starting off with the initial guess for my parameters, then adding something more to it, then adding something more to it, then adding something more to it and adding something more to it till I come to the final answer, right. So, that is one way of thinking about it. So, let us try and write this down a little formally. So, now I am going to see what I can do about this f. Let us for the time being ignore the tree constraints, right. We will come back to the trees later. Time being, let us ignore the tree constraints, right. So, what I really need is so just when I am trying to do this in a numerical fashion, I am just operating with a single data set, right. So, when I say f, what I really am looking at is a point in Rn. So, what does that mean? Right, f really means, okay, what is the value of f at x1, what is the value of f at x2, x3, x4, all the way up to xn. So, when I impose constraints on f, then this I will be restricting the kind of vectors I will see, but in general when I am talking about f in this context, I just mean like an n dimensional vector, right. So, it is a, or you can think of it as a point in n dimensional space, right. So, typically what you do is you start off with some solution, right, f naught, you start off with some solution, let us call it h naught, right. Right. So, you can think of it like this. So, start somewhere here, that is my f naught, right, and then I compute the gradient and move in the opposite direction, right. So, I take a small step in this direction. So, I come here, that gives me a new set of parameters, right. So, this is one theta, this is another set of theta, and this will give me another f, right. But instead of saying that this will give me another f, so I am going to say that, okay, this is one f, then I add something to it, right. So, that gives me the second f. So, what I am actually computing in every step is the amount that I add to the previous solution to derive my new solution, okay. So, I am confabulating theta and f here. So, what I have here is theta, corresponding to every theta I have here, that will be a f, right, corresponding to every parameter setting I will have, that will be a output vector f, right. When I change theta, these values will change, right. So, when I am here, I have one solution, right. So, when I want to go to here, that essentially means that whatever f vector I have here, I will have to change each of those coordinates by some value, so that I will end up here, right. Those values I change the coordinates by is my h vector, right. Is it clear? So, what we are doing here? So, what is the normal mechanism by which we will do this, right. So, I have been using the same example so far, right. So, steepest descent is something that will pop up, right. I mean, there are other ways of doing this optimization, right, but steepest descent is the one that we are all familiar with, the one that I have been using as an example here so far, right. Right. Since I have not chosen any arbitrary parameterizations for my theta, right, for the f I have not chosen any parameterization theta or anything, right. So, the parameters of f are the outputs at each one of the input points. See, the way I characterize my function f is looking at, okay, what will be the value of f at x1, what will be the value of f at x2, and so on and so forth, right. I do not have any other parameterization for it. So, instead of finding your dou L by dou theta, you actually find that I am writing it as dou L by dou f, okay. So, f of xi is essentially the output of f at xi, and what is f here? It is f m minus 1, because I am determining the mth stage, I am looking at the m minus 1th guess for my function, right. So, the steepest descent direction would be saying that, okay, so gm is the direction in which you have to move, because that gives me the direction in which the, or rather minus gm is the direction I have to move, because that gives the direction of steepest descent, right, and rho m gives me the step size I have to take in that direction, how large a step I can take in the direction. So, now how is rho m determined? This should look very familiar, right? This is exactly how we did the Ada-Boost derivation. Now people are thinking, oh, did we really do the Ada-Boost derivation like this? Yes, we did. Go back and think about it, okay. So, very similar, not exactly the same thing, but very similar, the same steps that we did, right. We first found out which way we have to change it, right, and then we found out what the step size should be, and the way we did it was, okay, I already have a classifier till the m minus 1 stage, okay, what should I do at the mth stage so as to minimize the error. So, this is exactly what we did. The idea behind each of the steps are same, the mechanics might have been slightly different, right. So, once I get this, then I do okay. Right. So, is it clear? People are with me so far? Right. So, whatever we are trying to do, right, is nothing. So, there are two different parts here, okay, if your people are getting confused. So, the first part here talked about boosting trees, okay. The second part here talks about taking some differentiable loss function and trying to do some kind of a stage wise process on it, okay. I just took your normal gradient descent procedure and told you that you can think of it as a stage wise process, like just like we did with boosting, you can think of it as an additive model, right. So, whatever you learn here, right. So, now the thing is how we connect up the two. I will somehow account for that later. I do not want to erase anything from the board, because what we are doing right now is connecting the two parts, right. So, I do not want to erase anything from the board. So, you can see both that and this while we are looking at this, right. So far, so GM GM is some kind of an unconstrained maximal descent direction. I do not have any constraints on f or anything else, right. What is the maximal descent direction? I essentially get GM. So, now what we are going to do is to say that, hey, all of this is nice, but I would really like some parametric forms for what I am doing, right, otherwise things become too complicated. So, what I am going to do is I am going to fit a tree. So, what I want to know is GM, right. So, if you think about it, so I really need to compute GM, and instead of doing this in this arbitrary unconstrained form, I am going to build a tree that approximates GM as closely as possible, okay. So, you should note something here. What is it you should note? So, for all this while I have been very carefully writing L for the loss function, because I am trying to keep this as generic as possible, right. But here I wrote a squared error loss function. okay, because it does not matter what is the problem that I am trying to solve, it does not matter what this loss function is, okay, because what I am trying to solve now is trying to approximate a vector, trying to approximate a direction, right, by a tree. Essentially I am always solving a regression problem here, right. So if you think about it, GIM is going to be some kind of a vector, right, GIM will be some kind of a vector. All I am trying to do is predict the value of that vector component, right. So I am just doing regression regardless of whether my original problem was a classification problem or a regression problem or what not. I could use any loss function here, right, I could use any loss function here. This is the crucial difference you should appreciate, right. For actually solving the problem, right, I could be using a different loss function here, okay, but when I am building the mth stage decision tree, all I will be doing is regression, because all I need to predict is what is that particular gradient descent direction for that input value xi. Right. So this is what I am going to do. Well, how am I going to go about doing this? Well, it depends on what this loss function is, okay. So if this loss function, so if the problem I am solving is say regression, if this is what I am solving, this is the squared error loss function, okay, this is not this, okay, this is that. So if this L is squared error, okay, then what do I get here is essentially what is this? GM. This is GM, essentially the gradient of the loss with respect to f of xi, right, the gradient of this with respect to f of xi is essentially the residual yi minus f of xi, right. So this is basically minus GM if you would think, correct. So now what happens if I am doing regression with squared error loss function and I am trying to do this gradient boosting, right. So I am trying to build a new tree that predicts the direction of the gradient. What do I end up doing? I end up predicting the residual. I end up predicting the residual. This is the residual, right. So I end up predicting the residual, and here what we said, if you are doing the squared error loss, pick the tree that best predicts the residual. So that was derived from just the basics of boosting, regular boosting, while here I am talking about a technique that can do boosting on trees regardless of what is the underlying loss function, right, but it does boosting using trees, okay. So that is the cool thing about gradient boosting, right. So you always are solving a regression problem as far as the tree is concerned, and solving regression problems using trees is very easy, right. You are solving regression problems using tree always regardless of this loss function. If you remember when we were deriving this boosting update, I said for squared error and for 2 class exponential loss the boosting form is easy, right. But now if you are doing the gradient formulation of it, okay, regardless of what you are doing with the loss function, you can still do boosting with trees. So that is why gradient boosted decision trees have become very popular now, because you can do all kinds of cool stuff with it. So what about this? Right, and suppose you are doing classification, let us take deviance as the loss function, right. People remember deviance, we looked at deviance multiple times, right, and it turns out that so what is this? If the ith class is gk, then it will be 1 minus that the data point xi is in class k, the probability of data point xk belonging to class k. So it will be 1 minus that, and if the actual class is not k, right, then it will be minus probability of xi belonging to class k. Okay, so this is like the ith component of it. This is ith component of my gi. Okay. So again what I have to do, I have to take this expression, plug it in here and do regression again. I will take this expression, plug it in here and do regression, right. So all you need to do is figure out what is the derivative of your loss function with respect to your f of xi, right, and then once you find out the derivative, you just do the regression with respect to that for each stage in your decision tree. Okay. So what will be my gamma j? This is gamma. Yeah. Gamma jm. What will be gamma jm? So earlier we said it will be just the average residual error in RJM, right. So in this case it is going to be, so once I have found out what the actual regions are, right. Once I have found out what the regions are, this is going to give me the regions, right. So once I find out what the actual regions are, I will do the following. So what have we done here? Okay. So earlier when we are finding out the when we are building decision trees, right. So the way we found out the regions, right, if you remember the way we found out the regions was we postulated a split point, right, and then for that split point we figured out what is the best gamma in the both half of the tree, right, and then we took a value for that, and then we kept looking at all the possible split points, right, the splitting variables and split points for all the possible combinations, and for each one of them we evaluated what the resulting residual error would be, right, and based on that we picked a split point. So here we are doing something different. When we are picking the split point, right, we are going to pick the split point such that the residual error in predicting the gradient is minimized, right. I am only predicting the gradient here, the residual error in predicting the gradient is minimized, but when I finally decide what is the output that I am going to give in each of the final regions, right, So in the regular decision tree building, by the time I come to that point I would have already solved the optimization problem, right. So I know what is the solution that I have to give, and it is the one same thing which I use for splitting criterion. But in this case, when I finally give the outputs, I am going to look at the loss function, right, of data points that fall in that region, okay. Look at what is already existing, that is fm minus 1 of xi, right, and look at what I need to add to bring up the output so that the loss is minimized. So whatever is the loss function. So when I am doing the loss function here, I will no longer be using the squared loss, I will be using one of these. I mean, this is squared loss, I could be using the absolute loss, or I could be using deviance, or whatever is the measurement that I want, right. I will use this loss function, the loss function I used there, I will use that here in order to figure out the outputs, okay. So you have to let this sink in a little bit. So it is actually a pretty cool idea, right. So I have somehow come up with a mechanism where I can use decision trees in a very powerful way, because finding regions while I do regression is very easy with decision trees, because we know how to use squared loss, and there are lots of tricks and optimizations that you can do when you are searching through with square loss, right. We looked at some of them, but there are many other things that you could do. So what I am going to do is, for all my tree growing part, right, I am just going to use the regression trick, right, and I finally have to give an output at that point, I will use whatever is the true loss function I want, right. That is why it is called gradient boosting. So I use the gradient at every point to boost my performance, right. So the way I fit my, so if you think about it, this might not necessarily be the most ideal way of doing things. Why is that? Right. So if I want to predict gamma hat Jm that truly minimizes, forget about the RJs, right, that truly minimizes the loss function, I might want to actually split the space in a different way, right, but I am using the gradient information to split the space. Then whatever splits I get, whatever regions I get by using the gradient information, I am using the same regions in order to reduce the error also, right. It is fine as long as I am unconstrained, right. As soon as I put in the constraints of trees, it is not entirely clear that the tree that you want for getting the representing the best gamma hat is the tree that you want for representing the best GM. Okay. It's a very subtle point, you have to think about it a little bit, but more often than not it turns out to be fine, okay, but there is really no guarantee that the best tree for predicting GM is the best tree for representing your gammas, okay, that are two slightly different things, but still it turns out to be fine, right. So all of this discussion collapses if you move to L being the residual, I mean the squared error, right. If L is squared error, everything looks the same, you already solved it here, that is a very easy thing to do. But what I want to point out is, with essentially the same squared error mechanism, you can build boosted trees for any loss function that you want. It can be regression, it can be classification, so whatever it is, you can build a decision tree. So one thing that you have to be careful about is that you do not overfit the things anytime, right. So you have to be careful about not overfitting the data, because you are only working with n data points always, right. You can build a very complex tree that will try to overfit the gradient for just the training data, right. So that is not a good idea. So try to keep your tree down, complexity of your tree down. In fact, quite often people choose a size of the tree a priori, and then you might actually end up adding more trees than necessary because you chose too small a tree, but at least you will avoid overfitting, right. And so that is it for gradient boosting.